Hello everyone, thank you for watching my video today. In this video we're going to take a look at integration and evaluating improper integrals. So there's a couple different types of improper integrals. We're going to look at all the types that we can figure out today, and we'll take a look at our approach to them, which is going to be involving limits. Okay, so just looking right here, these are the types of improper integrals we can evaluate. Either one or both of the limits of integration are infinite, or f has a finite number of infinite discontinuities on the interval. To get an idea of how to do this, let's consider this right here. And if we integrated that and substitute in, we would get this back, which we interpret as the area of the region. If we took the limit as b approached infinity, this would go to 0, so our answer would go to 1. This improper integral can be interpreted as the area of the unbounded region between the graph of f of x, the x-axis, and to the right of 1. So here's how we would approach improper integrals with infinite integration limits. If the upper bound is infinity, we would just take the limit as b approaches infinity. If the lower bound is negative infinity, we would take the limit as a approaches negative infinity of our integral. And if the bounds are negative infinity to infinity, we'd break it up into 2 and go from negative infinity to some number c, and then c to positive infinity. In the first two cases, the improper integral converges if the limit exists. Otherwise, we say the integral diverges. In the third case, the improper integral on the left diverges if either of the improper integrals on the right diverges. Diverging is bad. Basically, we just don't get an answer. That means converges means that we'll get some type of answer that our area is headed towards. Let's take a look at our first problem. Example 1. This is going to be an answer that's going to diverge, and you'll see what happens when that happens. So we have our integral from 1 to infinity of 1 over x dx. So we have an upper bound of infinity. So I'm going to write this as a limit as b approaches infinity of the integral from 1 to b of 1 over x dx. All right, so we have the limit as b approaches infinity of ln absolute value of b from of x from 1 to b. Got a lot of myself there. From 1 to b. So that's the limit as b approaches infinity of ln b minus ln 1. ln 1 we know is 0, so it's a limit as b approaches infinity of ln b, which is the natural log of infinity, which is going to go to infinity anyway, right? So that's why we say it diverges. It does not go to some constant number that we can say. It's getting closer and closer to. The second one, this is going to be one that we actually do have an answer it converges to. So let's take a look at this. So it's going to be limit as b approaches infinity of our integral of 1 to b of e to the negative x dx. So it's going to be a limit as b approaches infinity of negative e to the negative x from 1 to b, which we can write as limit as b approaches infinity of negative 1 over e to the x from 1 to b. Substituting in, we get limit as b approaches infinity of negative 1 over e to the b minus negative 1 over e, which we can simplify down to negative 1 over e to the b plus 1 over e. And if we put infinity in for that, we would get negative 1 over e to the infinity plus 1 over e. This is getting bigger and bigger, which means this is going to 0. So 0 plus 1 over e. So our answer here is 1 over e. So we say this integral converges to 1 over e. Basically what that means is it's never going to actually be 1 over e, but it's going to, as we get our upper bound closer and closer to infinity, our integral is getting closer and closer to 1 over e. Example 3. So again, our top bound is infinite. So we're going to set this up as limit as b approaches infinity of the integral from 0 to b of 1 over x squared plus 1 dx. And we should recognize that integral as the inverse tan. So it's limit as b approaches infinity of tan inverse of x from 0 to b. So we have limit as b approaches infinity of tangent inverse of b minus tangent inverse of 0. As we put infinity in there, we get tangent inverse of infinity minus tangent inverse of 0. Tangent inverse of 0 is 0. So it's just tangent inverse of infinity. So if you think about the tangent inverse graph, let's draw a quick sketch of the tangent inverse graph here. The tangent inverse graph would look like this. So we want to think about, all right, well, what is this horizontal asymptote that we're getting to? And it's actually pi over 2. Right? As the domain of tangent inverse goes from negative pi over 2 to pi over 2. So as x, or in this case b, goes to infinity, our tangent inverse graph would be getting closer and closer to pi over 2. All right, fourth example. Again, we have a infinite top limit. So we're going to start here by writing this as limit as b approaches infinity of the integral from 1 to b of 1 minus x e to the negative x dx. All right, and we are going to need to do this integral by parts. We have two separate integrals. There's nothing that we can do to substitute for. Sorry, two separate functions that we can't substitute for. So we're going to let u equal 1 minus x, and then dv equal e to the negative x dx. So du equals negative 1 dx. And v would equal negative e to the negative x. All right, so then I'm actually going to move this off to the side over here. I need some more room than this. So now I can rewrite my integral as a limit as b approaches infinity of 1 to b of uv, so 1 minus x times negative e to the negative x minus v du. So it'll be plus the integral of e to the negative x dx. Actually be minus because it's minus, minus, minus. So 3 minuses would make that from 1 to b. And we need to evaluate this from 1 to b as well. So this is already integrated per se. This is not yet. So we'll have to do that next. All right, so then our next step, limit as b approaches infinity of, if we put b in there, we would get -1 plus b times e to the negative b minus -1 plus 1 times e to the negative 1, which is all going to be 0 anyway. All right, and if we integrated this, we would get plus e to the negative x from 1 to b. All right, so if I just duplicate that, and then I change that last one, if I put b in, I would get e to the negative b, and then plus e to the negative 1. And of course, this here would be 0. Negative 1 plus 1 would be 0, so we can get rid of all that as well. Okay, so now we can rewrite this. I'm running out of room pretty quickly here. Let's move this over here. All right, so if I rewrite this as limit as b approaches infinity of b minus 1 over e to the b plus 1 over e to the b plus 1 over e. And now if I put infinity in, actually this is supposed to be minus, I'm sorry. Made a mistake there. Minus. Now if I put infinity in, to this one at least, it'd be 1 over 0, so I know that's going to be 0. To this one, we would get infinity over infinity. So if you remember from, I believe, Unit 3, we can apply L'Hopital's rule to that. So it's going to be limit as b approaches infinity of 1 over e to the b. I'm not going to write the second part because we already said that would be 0, minus 1 over e. Now if we put infinity in for b again, we would get 0 minus 1 over e. So our answer would be negative 1 over e. So again, we'd say that this integral converges to negative 1 over e as our top bound gets closer and closer to infinity. All right, what if, in example 5 here, both top and bottom have infinities? All right, so now we're going to split this up into two integrals. Well, before I do limits, I'm just going to split up into two integrals. Let's say we're going to write this as negative infinity to some number c of e to the x over 1 plus e to the 2x dx plus c to infinity of this same thing here. Okay. Now I'm going to write this as a limit. So it's going to be equal to the limit, well, actually, it's going to be two limits, as a approaches negative infinity of a to c of this integral plus the integral from c plus the limit as b approaches infinity of c to b of this. So again, we should recognize this as another arctangent integral where a is 1 and u is e to the x. So it's going to be limit as a approaches negative infinity of tangent inverse of e to the x from a to c plus limit as b approaches infinity of tangent inverse of e to the x from c to b. All right, now we substitute in, so limit as a approaches negative infinity of tangent inverse e to the c minus tangent inverse e to the a plus limit as b approaches infinity, tangent inverse e to the b minus tangent inverse e to the c. Important note here that there's nowhere to put infinity in there. So that's just going to be tangent inverse e to the c. Same thing here. That's going to be tangent inverse e to the c. This one's positive, this one's negative. So those two end up just canceling out. So what we're left with here is limit as a approaches negative infinity of negative tangent inverse e to the a plus limit as b approaches infinity of tangent inverse e to the b. Now we can substitute in, so we get negative tangent inverse e to the negative infinity plus tangent inverse e to the infinity. So this is negative tangent inverse of 1 over e to infinity, so 0. So that's just going to be 0 plus tangent inverse of e to the infinity, which is infinity. I'm just going to get rid of that and change it to infinity. And we already looked at that earlier today. As tangent inverse goes to infinity, that just goes to pi over 2. So this is going to be 0 plus pi over 2, so pi over 2.